In this lesson, we're going to be finding antiderivatives by the method of integration by parts. So how do we know if we're going to have to use the method of parts? Well, an indicator would be that in the integral we're trying to find an antiderivative for, we have a product. We have a product of two different types of functions. I think an acronym that's going to be helpful for you guys in determining whether you're going to proceed with integration by parts, an acronym, okay, that we're going to use is LIPIT. LIPIT. So L stands for logarithmic. Okay, if you notice that the integrand has a product of a log function and an inverse trig function, or any combination of these next few types of function, then you might want to try the technique of integration by parts. P is polynomial, x, x squared, 3x to the fourth. LIPIT, L-I-P-E, you probably see where this is going. That would be some sort of exponential function. And T stands for trig, trigonometric. All right, another acronym that you're going to want to use to help you remember the formula, okay, that we have. If once you've identified that when you find an antiderivative, you're going to proceed with integration by parts, you have to, in your brain, call up this formula. And that's not an easy thing just to kind of whip out. Okay, so this is the integral of some u quantity integrated with respect to v, and that's supposed to equal, this is our given problem, that's supposed to equal u times v, that product, minus another integral. So you can see in this formula that even though we're using integration by parts, my answer contains another integral, which I'm going to have to then proceed and integrate again. And the thinking is this might be very complicated, but once we use the technique of parts, that even though this is complicated, by the time we use this formula, this is going to be a simpler integral. This might be a good time to look at your little green sheet and look at that topic of integration by parts for any kind of clues there too. Okay, something else that I've heard out there that might help you as far as remembering this formula is this statement. If you know that you're going to, that's an L, if you know that you're going to proceed using the method of integration by parts, then you might want to remember ultraviolet voodoo. I stole this from somebody. If you can remember this, this will help you remember the formula right here. Okay, so if we think about the letters here, ultraviolet voodoo. Okay, if you're going to do integration by parts, then think about this first product. Ultraviolet, the product of u and v, and then voodoo, v, and then the do. So if you want to spell ultraviolet voodoo this way, that might even be better for you. Okay, so a little acronym to help you remember the formula. So for our first example here, we're going to integrate using the technique of parts. Okay, you can see we have a product of a polynomial function t and a trig function, cosine. All right, so as you look at the different pieces and components of this entire formula here, there's four different things going on. We have u, we have v, then we have du, and then we have dv. So there are four pieces to this this integration by parts method. Okay, so if we can set it up correctly, the UDV part, then we can use ultraviolet voodoo to help us integrate. All right, so over here, this is what I would recommend. Once you establish you're using parts as a method, okay, let's come over here and list those four things that I need to come up with. Okay, so I'm going to need to establish what is u, and that's going to be what's given to me here. So what part of this integrand is going to be u, so that du, the derivative, is pretty easy. Well, u could either be t or u could be cosine t. Both those derivatives are easy enough. And I also need dv, I'm going to go backwards here, back to v. Notice in the formula I need to have a differential here. So if I have a differential, I have to be able to integrate it back to v, so that's why I lead off with the dv here. Okay, so dv at minimum has to contain dt. All right, and then from there, Okay, do you choose, you know, to go along with dt? Do you choose cosine to go along with dt? Or do you choose t to go along with dt? Okay, so, but whatever I choose over here, I have to be able to easily integrate to get v. And note that once you get v, you're going to have to integrate it again. It'll take several examples for you to start to get the feel of how to allocate these 4 items within your problem here. Okay, but you might want to use this as a guide right here. Do I have any logarithmic part, okay, of this problem? No, I don't. Do I have an inverse trig? Nope, I don't. Okay, do I have a polynomial function? Yes, I do. Okay, so that's the first thing I identify. So for our establishment of u, you might want to use this in order, okay, to figure out what u is. So I'm going to go with that. I want u to be my polynomial function because it comes before trig. I'm not saying always works, but it's a good rule of thumb. All right, so u is actually going to be the polynomial part, t, which means the derivative is just 1, okay, with respect to t. So du is just dt. Okay, you'll see how all this fits together in a minute. Okay, so I need a differential here. Okay, so if u right here is t, then that means everything else has to be, that's u, this has to be dv to fit this formula. All right, so dv has to be cosine t dt. All right, so now let's integrate. To go back to v, I get back to sine. Let's see if this was a wise choice, or maybe u should have been cosine t and dv should have been t dt. Okay, so now thinking about my formula here, my integral u dv that I have here, and maybe I should just keep it t cosine, sorry about that, t dt, is equal to the product of uv. Okay, so I have to multiply these two. So that would just be t sine t, easy enough. Okay, that's part of the answer. No further action needs to be taken, minus the integral v du. So now it's minus v right here du. Okay, so now that we're in this step, just think about it for a minute. When I multiply here, I'm going to get an integral of sine t dt. And what you're trying to do is get to a point where this is easy to integrate because I have one more step with this technique of integration. So my final answer, t cosine t dt. Okay, the antiderivative here, well, if it goes back to negative cosine, if you want to bring in a negative and then pull out a negative, that becomes plus, and this gets replaced with cosine t. That's an indefinite integral, so I'm going to add a constant of integration. So integration by parts, use the formula, but notice that you have yet another integration to perform because it's part of the formula. And your objective is, using this maybe strategy over here, try and find VDU so that it's easily integrable. Okay, so we're done with this, finished, but what if? So y'all just watch. What if I had let u, in this problem, be cosine t? Okay, the derivative is easy enough. Negative sine t dt, which would have meant that dv would have been the t dt part. So the antiderivative would have been t squared over 2. Okay, then think about this formula. What we have to do is multiply these two together, v du, and integrate. Well, if I put this in one integral, I haven't made an easier integral. I've made it more complicated. So that wasn't the right choice for you. Not for you, but for you. All right. It's not always, easy to figure out what u is, but this Lipit order might help you with that. It's just going to take doing some extra examples. All right, so for example 2, what we want to do is once we discover that we're going to be using parts, we've already explored algebra as an option for integration. Nothing I can do with algebra is going to help me. We've tried u substitution. That's not going to work. We've identified this not to be an inverse trig integral. We know the method of partial fractions is out. There's not a fraction. An indicator is that you have a product of 2 of the Lipit functions. Okay, so then I'm going to come over here and go, all right, well, if I'm going to use integration by parts, I need u Then I need to differentiate u. I need dv, and I need v. All right, so thinking about the formula, we need to establish what is u and what is dv. And at minimum, this has to be dv. So u is either going to be x or e to the x, or maybe the product x e to the x. But I think that's what's got us into trouble, is having a product here. And as a matter of fact, this actually is a derivative that came from the use of the product rule. That's how we resulted in this answer. This answer was arrived at by differentiating using the product rule. So by using parts, we're actually undoing the product rule and getting back to the original function. All right, so lipid, L, logarithmic, nope, nothing there. I, inverse trig, nope. P, polynomial, yep. E is exponential, so typically polynomial would come before exponential, meaning come before what? Meaning u would be our polynomial part. Its derivative, dx. Because we want something here that when I multiply by v is easy to integrate in the formula. All right, so if u is x, this is u, then all of this has to be dv. So dv is now e to the x dx. All right, so that's okay, because I can integrate dv to get back to v, which is part of my formula that I need, and the antiderivative is just itself. All right, so when we can real quickly see that this product right here would be easy to integrate, I've just removed the product by letting u be x. Okay, I've found the derivative and made this problem easier. All right, so here's our problem. This is going to equal ultraviolet voodoo. Ultraviolet, that product, minus the integral voodoo, v-do, ex dx. All right, and we're going to have to integrate once more. The antiderivative here is easy. It's itself plus c. Okay, and remember, with all indefinite integrals, you could always check the result, your antiderivative, by differentiating. Okay, so over here, differentiating, I'd have to use the product rule, find this derivative, things are going to cancel, clean up, and you're going to end up with this integrand here. Okay, again, it just takes practice. So let's look at another example. All right, so let's establish what u is and dv is. U and dv. dv goes here. And its antiderivative goes here. So lipid, L, logarithmic part, you bet. I'm going to let u be ln(t). That derivative is 1 over t dt. So if this is u, if this is u right here, then t dt would have to be my dv part. You could rearrange it if you wanted to. Now let me find the antiderivative, which would be t squared over 2. Okay, so let's see if that's going to work out and give us an easy integral to integrate. T ln t dt equals ultraviolet voodoo. Ultraviolet. So whenever you multiply that together, it really doesn't matter what that is. So t squared over 2, I would probably put ln t on top here also. And maybe fix this up a little bit and put a 2 here. It just takes too much time for me to go back and take that out. Okay, minus the integral voodoo. Okay, well, look at what we have here. We're going to have a product. We can clean this up before we integrate. We have dt. Don't forget that part right here. Okay, let's do a little algebra here. T ln t dt. Oh, my goodness. This is going to be minus the integral of, what is this, a half t dt. So, and once more, and I should be there. That's ln. And this antiderivative, let's see, you'd go up to 2, divide by 2, so that would be 1/4 t squared. Plus c. Okay, again, you can always check your work by differentiating to make sure that you end up with the integrand here. All right, I think, let's see, that was example 3. I have 2 more examples, but too many for this one video, so we'll continue in the next one.